Okay, good afternoon and welcome. Thank you for joining us. How many folks are here to participate in the CodeBreaker Challenge? Okay, very good. How many people are here to help with the CodeBreaker Challenge? Okay, so all the folks in the back, thank you again, both from UTSA here as well as our folks from the National Security Agency. My name is Guy Walsh. I'm the Executive Director of the National Security Collaboration Center. How many folks are familiar with that organization? Okay, relatively new, but located over at the NPB over here. I'll get my acronyms right, having been another NBP over at the NSA side of the house. But I joined UTSA relatively recently, here in July. I had the opportunity to come here to stand up the National Security Collaboration Center and be part of the UTSA team here. And prior to that, for the last 9 years, I had the opportunity to work with the folks in the back here from the National Security Agency, working back at Fort Meade on the U.S. Cyber Command side of the house, which is the Title 10. So most of you, again, are familiar with the fact that the National Security Agency is a Title 50 intelligence community organization, code breaking, code making all across the board there. And without that capability and without without the National Security Agency hosting the Title 10 organization that I was part of, what's called U.S. Cyber Command, we would not be anywhere close to where we are today as a nation in terms of the security in that piece there. So the director, Eric's director here back at the fort, General Paul Nakasone, also happens to be the commander of U.S. Cyber Command in terms of that mission space there. So with that, let me say welcome again to our folks from the National Security Agency. This is the rollout of this year's cyber exercise that we're about to do with the CodeBreaker Challenge. We are very fortunate today to have with us Mr. Eric Bryant, the developer of the exact challenge, to talk to you about the challenge and where we're going to go from there. For those that know, last year this event was taken by none other than Benny the Beaver. Okay, so Oregon State University out of Oregon was the winner last year. I am sure Rowdy is hungry here today and ready to take that to the next level. So without any further delays here, let me introduce the developer. Oh, let me say one last thing. So last year, what you will find is everything you're going to be able to do during this exercise in terms of whether it be reverse engineering, data analysis, the programming, all those aspects really is an opportunity to tie to what I will call the real world situations and real world what's going on there. So part of this isn't just let's make up a game that seems fun. It's really to say let's look at these challenges that we have out there that have no exact solutions. Last year's situation was what was called ransomware. Has the state of Texas had any issues with ransomware maybe recently? But those type of things. So what you will find is on each and every one of these, of something such as the CodeBreaker Challenge and the programs that the National Security Agency does with universities and with industry, really do tie very closely to those real world problems that we have there. And so the person who's going to bring us into that world, bring us into the CodeBreaker exercise with our Tech Talk today, Mr. Eric Bryant. So Eric, it's all yours.
All right, thanks for that introduction. It's good to be here in Texas to talk about CodeBreaker Challenge, so thanks for those on the live stream for tuning in. So I'm Eric Bryant. I'm a technical director within our cryptanalysis organization, and as Guy said, I'm also the lead developer on the CodeBreaker Challenge. So just out of curiosity, how many of you have actually participated in a previous CodeBreaker Challenge? Anybody? You? One? Can you hear me okay in the... Okay, sorry, I will project. So yes, we have one person. And are you all planning to work on this year's challenge? Awesome. All right. So what we have planned for today is I'll start by introducing this year's challenge, kind of walk you through what we have planned, what the different tasks are. Then we'll segue over and I'll give you some more technical background to introduce you to the different types of technical areas that you'll be exposed to as you're working through the challenge. And then at the end, I'll talk about last year's challenge and how to solve some of the final tasks for that. We also have, if you have the Slido app or you have that pulled up on your web browser, or for those in the live stream, if you have any questions throughout the presentation, you can post your questions there. I believe it's UTSA CodeBreaker 2019 is the room. So feel free to post whatever questions you have. And as I'm going along here, if you have questions along the way, feel free to interrupt me. One of the things I wanted to start with is our director actually made a little introductory video, and so I'm going to start off by playing that, and then we'll get into the briefing.
Are you ready to tackle difficult problems like we do at the National Security Agency every day to keep our nation safe? If so, you're ready for CodeBreaker Challenge. Hi, I'm General Paul M. Nakasone, the Director of the National Security Agency. I'm excited for this year's CodeBreaker Challenge. We started the CodeBreaker Challenge in 2013 with only 5 schools. We've grown their program to over 2,500 students across 350 colleges and universities. It's designed to give students like you an experience of what we do here on a daily basis, from cryptanalysis to reverse engineering, from exploit development to network protocol analysis. This year we're going to focus on mobile security threats. Are you ready to test your knowledge and skills to develop multiple exploitation capabilities against a secure messaging app? I'll be tracking your progress and those of the top universities and colleges as you move through this competition. So enjoy the challenge. Consider working on our team, the A-Team. So check out job applications at nsa.gov. Good luck, and I look forward to seeing you in the near future.
All right, I'm going to shift over to the PowerPoint. There we go. All right. So that was the intro. All right, so what is the CodeBreaker Challenge? So as you saw the director state there, this is something we started back in 2013. It began fairly small as a pilot with just a handful of schools. But what we really wanted to do was to give students the opportunity to get some real hands-on experience, more from, I guess, a cybersecurity practitioner perspective, which would sort of complement what you get day to day in your classroom. So it's an annual competition. Every year we come up with a unique storyline. And so we've done everything from designing a remote controlled IED explosive device where students were working towards disarming and ultimately breaking the bomb, to we had a simulated SCADA system that had been attacked by a botnet one year. And then last year we had the ransomware, and I'll talk a little bit more about that one at the end. This year's challenge is actually about a mobile application. So as I go through, I'll talk in a little bit more detail about that. It's opened up nationwide. So in 2015 is where things really changed. That's when we first launched the website and opened this up across the country. So if you look at the top finishers from last year, we had Oregon State that came up on top, Georgia Tech in second, and so on. Yeah, every year it seems that you get more and more schools that have been signed up. I believe we had 377 last year in total that participated. So this is our app logo, Terror Time. This year's story, what it is about a terrorist organization that has developed a new secure messaging app, right? So think about WhatsApp as a good example. So this is an end-to-end chat application, and in the storyline, they're using this to do their attack planning. So at the beginning, in a real-life scenario, an app like this wouldn't be something that you would find on the Google Play stores, right? So one of the initial challenges would be, well, how do you even get this type of app? And so what you'll see when I start talking through the tasks, one of the very first things that you're going to be doing is analyzing a packet capture to try to extract it out of a download. And ultimately, your goal is we want to build these 3 main exploitation capabilities. The ability to spoof messages, in other words, make it appear as though the message is coming from a different user. This type of capability would be useful if you're trying to disrupt a terrorist planning an attack. User masquerades, the ability to log in as another user and download their messages and see what those communications are. And finally, the ultimate goal is to be able to decrypt any message sent within terror time. So all the messages that are sent, so we're running an XMPP server. So all of the messages, there's a TLS connection to the chat server, but the messages themselves are end-to-end encrypted underneath that TLS layer. So what you'll be, when I say message decryption here, I'm talking about that final layer with how those messages are encrypted. Another part of the challenge is actually discovering and thwarting future attack plans. So to kind of enhance the whole story and experience here, when you sign up for the CodeBreaker Challenge, you'll have your own unique app and build and basically your own miniature terror network that consists of several users. And there are unique conversations and attack planning discussions that have already occurred within terror time. And so as you go through and you're solving these tasks, that's part of what you'll be submitting along with your answers are what some of these plans are, which the only way to actually get to that point would be through solving some of these tasks. All right, so if you look at what are some of the key skills that we emphasize, at its core, CodeBreaker reverse engineering and cryptanalysis have always played a central role in all the challenges that we roll out. Network traffic analysis is another one of those areas we try to include every year. Beyond that, we like to introduce other types of areas. We've had memory forensics in the past. Last year we had blockchain technology with the ransomware. This year we have a mobile app. So Android app analysis is going to definitely come into play. I already mentioned crypt. Binary reverse engineering. I specifically call it binary reverse engineering. In this scenario, you'll be both reverse engineering native codes, in other words, code that is compiled to a native architecture, but also the bytecode that's part of the Android app. And so you'll have two different levels. It's a little bit easier reverse engineering Java bytecode because there's more information that's available to you as the reverse engineer. But certainly in the final task, you're going to be doing more binary reverse engineering. And then vulnerability analysis. So vulnerability analysis is really underpins the majority of the tasks. Well, in particular, starting at task 4 through 7. This is looking at the code. So when you are studying the code and you're doing your reverse engineering, ultimately what you're looking for are, understanding how something works. That's the essence of vulnerability analysis. How does something work? What are some of the assumptions that a developer has made, whoever designed the app, and how might those assumptions be violated? How could you take advantage of that and exploit that in some way? So vulnerability analysis is very key, and that's kind of part of reverse engineering and the process that you go through. And then exploitation development, that's closely coupled with your vulnerability analysis. This is once you've actually found a weakness, you say you have an idea or maybe a theory about, hey, I think I could exploit, masquerading as this user by doing X, Y, Z. The exploit development piece is going to actually be trying to implement that and test it, and there's hurdles and challenges that you'll encounter, going through that process as well. All right, so let's get into the different tasks for this year. So the first 3 tasks, and we kind of outlined this on the website as well, these are the first 3 are really meant to be introductory tasks, helping you get started. The end result of once you've got through the first 3 tasks is that you'll have the terror time APK file. APK is this type, an Android app. It's APK, Android package. You'll have an APK file. You'll have a couple user accounts and credentials that you would have recovered, and you'll have figured out what the server addresses are for both our XMPP chat server as well as our OAuth server, and I'll talk more about OAuth here in a little bit. So at that point, you'll be able to play around with the app, install it in an emulator, send messages back and forth just to see how it all works. Then really beginning with tasks 4 through 7 is where the difficulty is going to get ramp up quite a bit, and where you're getting more reverse engineering and the other topics I mentioned. So really at the beginning, in the storyline, there's been because we don't even have the application yet, there's been a military operation where collection gear was forward deployed. And they've captured a bunch of traffic, and so you're doing some network traffic analysis and using a tool like Wireshark, for example, to extract an APK download, as well as some user credentials, so that you could actually log into the service. Task 2 then is taking a look at that file that you've extracted, looking at some of the app permissions, and getting some basic information about how the app is signed. This is just meant to kind of introduce you to the layout of an Android application and some of the contents that are there. And then task 3 in the story is that we've actually arrested one of the terror cell members at a port of entry, and we're able to get his laptop and device. And one of the things recovered from that device was a SQLite database. And so on the website, you would download that database, and your task for the third task is basically figure out what's the IP address of the servers, right? So like I said, at this point, you have everything you need to actually log in and use the service. Okay, now things start to get more interesting with task 4. So now you've got this SQLite database, but then you'll discover that there's a lot of the data is actually encrypted in the database. And so what you need to do with this task is figure out how's the data encrypted, and try to develop a method for recovering a PIN. So when you first load up the app, after an app is registered to a particular user, one of the things they set is a PIN, and so you need to figure out what a valid PIN is and recover those credentials, this is where you'll start to get in. This would be the first task that involves reverse engineering. Once you've recovered that, then you'll need to figure out how to actually make use of that to access that person's account and read some of their messages that they've had with their other terrorist members to figure out some details about an attack that's being planned. Okay. All right. So then with task 5, now this is where you need to do some analysis to figure out how do you actually log in as another person, right? So you have at least one set of credentials that you've recovered, task 1 from the packet capture. You had the credentials that you were able to figure out in task 4, but now we want you to come up with a way of, as any user, without knowing their credentials, to come up with an attack to actually be able to masquerade and log in as those users. You wouldn't be able to decrypt their messages because, like I said, they're end-to-end encrypted, but that's the goal of that task. Task 6 is actually broken into 2 parts, 6A and 6B. The ultimate goal here is you're developing message spoofing. So 6A, that's the goal, is that if using your masquerade capability, you can log in as a user, and you want to be able to send a user to somebody else. But critically, you want to, number 1, make sure that you can decrypt any reply that the user sends to you. And you want to make sure that the person you're masquerading as never sees any evidence that somebody else logged into their account and were sending these messages. The trick there is, like, any message sent is technically stored on the XMPP server. Now, granted, it's encrypted, but that's part of the challenge for 6A, is figure out how do you spoof messages and make it so that the real user never sees, next time they log in, they never see reverse engineering. But what I hope to, my main goal in this part is to introduce the tools and some basic techniques that will help you get started, and that way you can kind of figure things out from there. On the network traffic analysis side, there's 2 main tools that I think you'll find useful this year. One is Wireshark. Wireshark probably is the most commonly known tool, I would say, of system. Lots of nice features in terms of what you can do. It's actually a pretty sophisticated tool in terms of advanced like filters and other things that you can write to do your traffic analysis. But yeah, the traffic interception manipulation is really where Burp Suite would come into play. So on the network side, those are the two that I would recommend. And we have at the bottom here, there's some download links. I should note that these slides have actually been posted on our under our resources section now, so don't feel like you have to write down every web address that you see. You can go to if you go to our website and click resources, you'll see a PDF copy of these slides. All right, moving on to the reverse engineering. How many of you have heard of Ghidra, actually? Okay, yeah, that's good. So Ghidra, this was a big announcement, big step forward, I think, for NSA. This was a tool that we launched at the RSA conference this year that we open sourced. But Ghidra itself has actually been around for quite some time. In fact, it was one of the first NSA tools that I used when I started, about 10 years ago. But it's a very powerful disassembler. If you've used any of these other two tools, like IDA Pro or Binary Ninja, functionally there's a lot of similarities in terms of how you interact with the code and what features that it provides. One of the things that's really nice about Ghidra is that packaged in with Ghidra is a decompiler. So that can definitely make your reverse engineering easier when you can take that low-level assembly and then view it in a source code. Now, decompilation is not perfect, of course, but it can be a big help if you're trying to get the gist for what something does. And best of all, Ghidra is actually free, so you can I have a web link on a future slide of where you can download it. But when you do download Ghidra, bundled in with the distribution is a lot of documentation. So there's actually a couple classes that are part of that documentation. So if you're brand new to reverse engineering, what you could do is download the tool, check out the docs, and work through. There's a beginner class, there's an intermediate, advanced, and then I think an advanced developer. Because one of the things you can do with Ghidra as well is develop custom analysis scripts and modules. So this can be quite handy if you're in the course of your normal job or research, doing reverse engineering, and there's certain tasks that you want to automate that are repeatable. You can write a Ghidra script and load up a binary and just run it, or you can actually run it from the command line in a batch mode. So there's a lot of nice things you can do in Ghidra. Same with IDA Pro and Binary Ninja. Both of those do have a free version that you can use. And people have different preferences. I mean, they're all great tools. But I think Ghidra is the only one where you get an actual decompiler to use. IDA, I think it's a few $1,000s for that. So a few general tips. A couple, well, first of all, I'll mention, if you go to our website, the CodeBreaker website, under our resources tab, you'll see a series of lectures and some assignments that we have posted. This was from a class that we did with a couple of schools a few years back, and so it's actually, I think you'll hear my voice on all the lectures talking about. So you can get a little bit of an introduction to reverse engineering that way. But just in terms of some general tips, I think what's very easy to do when you first start to reverse engineer is waste tons of time. And what I mean by that is when you first load a binary into any disassembler, you quickly discover there's a massive amount of assembly code that's there. And it's very easy to start going down rabbit holes and trying to explore all these different paths. But there's a good chance you're just looking at code that doesn't matter at all for what you're looking at. And so developing the skills to more quickly find the code that you care about or what it is that you're trying to figure out is really important. And so that's where things like strings or other clues come into play. Like for example, when you run a program and it prints something out to the screen, well, whatever it prints out as a string, that string has to be compiled into the binary somewhere. It's going to get compiled into a data section, and there's going to be a cross-reference to that somewhere in the code. It's going to be moving a pointer to that string into a register and then displaying it. So if you examine the strings that show up in the disassembler, you can just click on it. It'll take you to that string, and then you can see, okay, well, what areas of code cross-reference this string? You can then just go to that area of the code, and you're going to be in the general area that you care about. You'll probably either do look backwards to the code, and so when you get to the, for a given method, you can see, well, what all functions call that method, right? And that's how you can kind of trace your way back and kind of get your bearings within the binary. And I think that's a really important skill to develop, is to leverage those cross-references that the disassemblers give you to kind of navigate and familiarize yourself and avoid going down these rabbit holes. Kind of along those lines, function names and their symbols in a binary, that can tell you a lot, right? Developers generally don't randomize their function names, and so if there's still symbol information, then that makes things a lot easier. In apps being Java code, Java bytecode, there's even more information available to you in terms of your reverse engineering, and that's because that code ultimately has to be JIT compiled at runtime. And so there's a whole slew of metadata about the exact names and variable names and fields and all this stuff that you would not have at all in native code, which is why things like Java are much easier to reverse engineer. Typically, apps that are deployed, not all, but most of them end up getting run through an obfuscator. So if you've ever done Android analysis previously, what you'll see is you'll load it up, and there's this mess of names that are, like a single character, class A.A.A.B or something. So you can't really glean much from when it's been obfuscated in that way. We chose not to obfuscate our app in that way, just because, the goal wasn't to make it annoying to reverse engineer, and we wanted the Java reverse engineering to be more kind of an initial introduction to reverse engineering. The much more complicated reverse engineering you're going to get plenty of when you get to the native code. But I just wanted to mention that because you will see that in a lot of apps that are available commercially. The other tip is make use of Google. There's a lot of good lectures, tutorials, manuals. For x86, Intel has very detailed manuals. Probably tells you more than you care to know about every single instruction. But it is a really good resource, and it's useful to get to learn. If you've never looked at a processor manual before, that in itself is a useful skill, just to understand exactly how all the different instructions work. So this is where you can download Ghidra. There's also this cheat sheet that's pretty handy in terms of using the tool. And like I said, inside it comes down as an archive. When you extract it, just look for the docs folder if you want to find the classes that I mentioned. Okay, so moving on to Android applications. So Android applications get distributed as these APK files. There are some new things that Google's doing with these app bundles. Ours, we're using an APK package for this, which would definitely be the case if there was an indigenous app, because they're not going to be putting Terra Time on the App Store. But the APK, it's basically an archive. You could actually run a zip on it, and it'll expand to directories, and you'll see all the resources. You'll see the images. You'll see the .dex files. That's going to be where your bytecode is, so the code that you actually want to look at. You'll also see a JNI libs. That stands for Java Native Interface. So there are a couple native libraries that you'll see. One of them is libterratime. Probably would be worth taking a look at that one. Very good resource, the developer.android website there. As you're looking through the code and you want to know what a particular API or method does, you're going to be able to find it here in exhausting detail. But pretty much if you just type any kind of method into Google, you're going to see Stack Overflow and everything, so make use of that. Key point for this year's challenge is that you'll want to run it in an emulator. So I did mention that there are native libraries. We built native libraries for x86 and x86 64. Part of that is just because we assume everybody's going to want to run it in an emulator, and you're not going to want to emulate ARM on your x86. That'd be super slow. And we also didn't expect people to necessarily install it on their actual device, since you're really doing more analysis of the application as opposed to just chatting up your buddy on Terror Time. But we do have some setup steps that are on the resources page. It's pretty easy. I mean, basically if you install Android Studio, you can set up your path variables to point to their platform tools, and then it's just a matter of running like ADB install and then your APK file. So it's pretty easy to get started, but that's sort of how we expect people to actually be running the app. And there are a lot of, as with binary reverse engineering and all these things, there's a lot of great tools that you can leverage. I mentioned Android Studio already. That's sort of the main developer tool. If you're building an Android application, you're using that. And packaged with Android Studio, you get the emulator and everything. And it's very easy to build. You can build whatever kind of Android virtual device that you want. I think for our development and testing, we were typically doing like a Pixel 3 x86 64 device that we would just build. And then when you run the emulator, it looks like that device that pops up on your screen, and you can click as if you were tapping in the app. I haven't used this one because I don't really run Windows, but the Visual Studio emulator is another option that, if you do run Windows, you want to try that out. I believe it's free. That's on I would say the dynamic side, so actually running the application. Jeb and Ghidra, I mentioned Jeb here. So Jeb is very specific to Android app analysis. It is a commercial tool, but they do have a free version. The free version does not decompile code. That's one of the limitations of the free version. If you want the professional version, I think it's a couple $1,000s. But the free version, it is a nice tool in that you can load an APK, and it's aware of all of the different files and the things that get packaged in with an APK. And so Ghidra is meant to be a general purpose disassembler. Jeb is a very specific Android specific tool, and so you're going to see a difference in performance loading an APK into Jeb versus pulling out a DEX file and trying to load it into IDA, Ghidra, or any of the other tools that are general purpose. Part of that is going to be a difference in how those tools disassemble programs. So like a typical disassembler is going to be doing a recursive traversal through the code as it's discovering the native code and coming up with different cross-references and all those things. If you're targeting specifically an Android app, disassembly is very easy. You can do a linear pass over the bytecode and produce a perfect disassembly. So Jeb, for those reasons, is going to be more performant for just loading in an APK. All right, I wanted to talk a little bit about OAuth, because OAuth is something that you will encounter. We're actually running our own OAuth server in this case. You've probably, if you've never heard of OAuth, you've probably actually used it, and maybe you just didn't know you were using OAuth. This is where you can essentially grant other third-party apps access to your data. So if you ever have one of those little consent dialog boxes, it's like, do you consent to let Google or such and such technology access your, say, Facebook contacts? Or under the hood, that's using what's known as OAuth. In Terror Time, we've implemented somewhat of a bespoke implementation of OAuth, in that it's using OAuth, but in a sort of a non-traditional way, in a way that makes sense for the Terror Time ecosystem and how they're set up. In Terror Time, because with OAuth, the way OAuth essentially works, and I have a diagram that will make this clear on some subsequent slides, is you get a unique token basically from the OAuth server after you've authenticated. Normally there'd be a consent step. We don't have the consent step. And normally if a mobile application was using OAuth, there'd be a single client. What's a little different is that everybody who registers for CodeBreaker, you're actually getting your own unique app. Everything is unique per student. And in Terratime, they're using OAuth as not just like an authorization, but also as an authentication mechanism. So that the idea by the Terratime developers, in the storyline, is that having their users not come up with their own password, in other words, using a random big token, would be more secure than them having their, like a password that might be guessable or brute force. So underneath the hood, when it's logging in, it's actually using the client ID and an OAuth token to authenticate users. And so part of what you're going to have to figure out is that indeed the case that it's more secure than a normal user password as you're going through. But OAuth, all the communication itself, it's over TLS. These are the main roles. So if you read the OAuth spec, they'll talk about the user, the client, the server, which the servers, you have your resource and authorization server. The next slide makes it a little bit more clear. This is how things look within the Terratime environment. So here's your terrorist user. He wants to use X as a service. So you have the app. The app goes to request an access token from the authorization server. So this is our OAuth server here. Requesting a token, there's going to be a client ID and a client secret that is transmitted in that step. If that's correct, then the server is going to be issuing an access token. Like I said, there's a consent step that we're not using within Terratime, so that's not reflected here. And then, so the app gets that back. So now the app has a token, and then it goes to request. So generically speaking, you'd say, I want to request this resource. What's actually happening in this case, the quote resource server is actually our chat XMPP server. So it's saying, okay, I'm going to log in. The chat server then validates that token and says, yep, token's valid, or nope, token's not valid. These tokens have time expirations on them, so they're not good indefinitely. Assuming all that works, then at that point, the client's authenticated, and they can use chat within Terratime. So that's sort of the high-level flow. And most of this closely matches, I think, what you see OAuth in practice, minus the consent step, and sort of how things are set up a little bit differently, where we're kind of using OAuth as also a way, as part of the authentication and access control process. All right, so to get started, if you want to sign up for the challenge, this is our website, codebreaker.ltsnet.net. All you really need is a .edu address. And the way it works is, I guess I should have mentioned this at the beginning, every task is worth a certain number of points. So as you're going through and you're working through these different tasks, when you solve a task, your school is awarded those points. And so we have a leaderboard, and you'll see tasks 1 through 7. And you'll see basically the number of students at each school that have solved each task, and then there's a total point total that school is awarded. And so that's how the schools will kind of move up and down the leaderboard. We associate you with this school based on your email address, so that's where that comes into play. At the end of the day, we want this to be a fun challenge, but also a good learning exercise as well. So the challenge is going to run through January 10th. That also kind of makes it easier so that it will fit in with your busy school schedule. So any questions about CodeBreaker, either this year's challenge, or I can kind of also give you a behind-the-scenes view of what goes into making the CodeBreaker, or just any questions. After this, I was planning to go through solving last year's, but Kathy? Oh yeah, good question. So if if you send us an email, the codebreaker at nsa.gov is our will reach all of us on the team. And so if you let us know your school's domain, so whatever the domain suffix is and your email address, then we can whitelist that domain, and then you'll be able to register, and your high school will show up from there. The only thing, like, we don't whitelist, like a gmail.com, just simply because then anybody could sign up for it. And we wanted to keep it sort of academic focused. And we do open it up in the springtime. The past 2 years at the RSA conference, we've just opened it up to everybody. But we like to keep the initial launch kind of more academic focused. So, all right, cool. Well, I'll shift now to the walkthrough. So I have a link here in the slides, so if you're interested to kind of read through in much more detail on this, I've pulled up on the system over here, and I'll show you a couple kind of zoomed in images and pictures to guide as I'm going through the walkthrough. But Jonathan Armour, the past 2 years, has actually written a really detailed, great blog. He's solved the past 2 challenges, and so he's written these blogs, and we read through them. It's like, well, it's probably actually better than we would write up if we were writing up how to solve it. And so, yeah, so the link's there, and I will pull up a couple images. Okay, so, oh, is that not showing? Is there a different, oh, that's interesting. Give me 1 second here. I'm having to scroll off screen. There we go. Now it's working. I don't know what happened. Okay. All right. So in the 2018 challenge, the theme was about a ransomware attack. And what made it somewhat unique is that the ransomware, so once a host was infected, the ransomware would actually create these smart contracts that would be deployed on an Ethereum blockchain. So Ethereum, if you haven't heard of that before, it's a contender with Bitcoin. It's pretty popular. It's not the most popular one like Bitcoin, but if you've heard of things in the news like initial coin offerings and things like that, many of those are actually on Ethereum. What we found interesting about Ethereum is that you can actually run executable code, and that's what they're called, smart contracts. But Ethereum, there's an actual virtual machine. So if every node in the Ethereum network is running a VM. And so if there's a transaction, so calling a method on a smart contract is a transaction on the blockchain, which might sound kind of weird, right? But essentially, that transaction calls that code, and so then every node then is actually running the same code. It's getting a result, and that result is mined back onto the blockchain. Writing the smart contract code is interesting from a number of different perspectives, but from a looking at the security concerns, there are some key differences that are important to understand. One is that being the blockchain, everything is in the clear, right? Everybody can read, and which is sort of the idea behind blockchain. Everybody can see what's on the blockchain. And so there are no secrets in that sense, right? If you had a contract that was storing I don't know, a number between 1 and 10, and somebody's like, submit your guess, what do you guess the number is going to be? Everybody could, if they knew how to read from the blockchain, they could just read the state of that variable and say, oh, this is the, unlike a program that you're running, or that might be running on a server where you have no idea what its internal state is. You do in the Ethereum case. And so the idea behind the ransomware is that this criminal group essentially wanted to maximize their chances that somebody would actually pay the ransom. Which kind of makes sense if you think about it from a kind of a game theory perspective. You have somebody who does the initial attack. They want money, right? The person on the other end obviously doesn't want to pay, so they're going to try to find any way they can to either get around or screw the person who's attacking them. And so nobody kind of trusts the other party. But having a smart contract is a way of having, exactly what's going to happen. It's not a matter of, you get ransomware on your system and somebody sends you a random Bitcoin address and says, hey, pay this, and then I'll give you the key. Well, how much confidence do you have that you're actually going to get that key after you've paid them, right? You don't have a whole lot. However, if you can see programmatically and you can review and you know exactly what code is going to execute when you pay that ransom, and you know that in this case, if the key that is given does not work, that you actually get your money back, then that increases your confidence, and that you could that you will, if you do actually pay, that you would get your ransom. And so the goals, the objectives in the 2018 challenge is that to first of all figure out, well, how can you get your key back without actually paying the attacker, because you don't want to give in to their demands, and ultimately, how can you, is there a way of not only getting your key back, but draining all of the money they've collected from victims and paying all the victims back? And so that was actually the final task, was to find and exploit some vulnerabilities in their smart contract to drain all their funds, pay everybody back, and win, so to speak. So I zoomed into, this is on Jonathan's blog, and I thought he did a good job kind of highlighting what the process looked like for when you'd be infected with the ransom. So down here you have your bad guy. He infects the victim's computer. He exfils. There's a encryption key generated that he exfils and deploys this ransom contract. Okay. The ransom contract then, all right, I should back up. There's 3 smart contracts that are involved in all of this. Every victim has their own ransom contract that's tied to them. The ransom contracts are registered with an escrow contract. So when you're paying into this escrow contract. And then there's this registry contract that is basically, there's a single registry contract that's sort of managing this whole ecosystem. So in the challenge, everybody actually had their own escrow contract. I think if this were deployed in practice, you'd probably have one escrow and then all your ransoms underneath that. So, but in the CodeBreaker, everybody had their own escrow and a bunch of ransoms, and there was a single registry. So, the ransom gets deployed. It calls register victim in the registry contract. And then there's this authentication event that's submitted. And so this was another thing that we designed in, because as I mentioned before, nothing you do on the blockchain is private. So therefore, you can't put secret information on there and expect it to remain secret. And so for that, we actually developed this autonomous crypt oracle that is simply watching the blockchain for different events. And this was one of them. When an auth event gets emitted to the blockchain as part of a transaction, the oracle sees that, and it can then take some action based off of the data that's put in that event. So in this case, what the oracle is authenticating is we made use of one-time code. So I'm sure you've all experienced this, right, where you're logging into some site and you get a 6-digit code. So those are called time-based one-time passcodes, which is essentially an HMAC with a certain way of deriving the key from that. Well, we used TOTP codes as a key for deploying the ransom contracts. In other words, the attacker, thought he was clever in that, okay, I want to make sure that any ransom contract is one that I deployed, right? So his actual key would have been in this crypt oracle. That way it's not on the blockchain. So if the authentication succeeded, now the oracle does a transaction with the registry contract. So this is a separate transaction on the blockchain at this point. It calls back and with a success or failure of that registration. And then it both calls a callback function into the escrow contract to say, hey, I've registered this ransom, it's good, and gives it the address. And it also calls back to the ransom contract and tells it to register. It tells it the specific escrow to register with. And that kind of completes the process. So at that point, the ransom's been registered, and it's associated with a particular escrow contract. Okay. So in terms of how you okay. In terms of how you can actually get away without paying the victim. So this was task 6 by this point. So I didn't go through the earlier tasks because they're kind of like leading up to this point. And one of the earlier tasks, you would have reverse engineered one of the binaries to find the one-time passcode key. So in the story, the ransomware had cleaned up a lot of its artifacts, but there was still a shared library around. And in that shared library, you could recover the key. Once you know that key, then that means you can generate your own TOTP codes. Because again, it's like an HMAC computation. And so if you know the time, then you can figure out what a valid code would be, which means that you could actually register your own contract. And that was the key insight. The vulnerability was that in the escrow contract, there wasn't a check to see if the victim ID had already been registered. And so one of the things, you look at this code, this code here is called, the language is Solidity. You can define these modifiers to functions on your smart contract that have restrictions. So you can say, only like this person or this address can call my method. That's how you can build in some security. So in this case, it's saying only an authenticated ransom. So think back to that diagram I had earlier. Only a ransom that's gone through that whole process and is registered could ever call this method, which is probably why there was not a check to see if it's already been registered, because in a normal situation, this would not be an issue. But you'll notice that this is basically writing in a new victim to a hash map, and the key observation here is that, as you see here, you get to set, the ransom contract gets to set the amount of the ransom. It's driving that process. And so once you've figured out how to generate your own TOTP codes, and therefore you can deploy your own ransom contract, you could just deploy your own ransom contract, get through that. You could authenticate it correctly because now you've been able to generate the correct one-time code. But then you could call this register ransom, which is going to overwrite the entry in the escrow for the real ransom contract, but you can set whatever amount you want. And so basically you could set 0 as the escrow amount, and then when you go to do your transaction to decrypt, or to get your encryption key, it will have thought, well, yep, he paid the ransom amount. And so that was the main weakness in here. There's actually a lot more code, but this is kind of zeroed on the kind of the key vulnerability. If you go to this blog here, there's a lot more description and he outlines a few other ways, other little attacks that you could do as well. But that was the essence of task 6, was realizing that you could deploy your own ransom and with a different value. So getting to the final task, one thing that's important to understand is how does the flow look like when you're actually going to pay the ransom. So what we have is, you have your computer over here. It calls pay ransom. So now you're interacting with the escrow contract. The escrow contract calls into the ransom contract and says, okay, give me your key. So the idea is that this escrow contract is this intermediary, right? The ransom is per victim. The escrow is like, okay, hey, I've received a payment. So the escrow is verifying that the payment matches what was registered. So on the last slide, last page, you saw how the ransom amount gets set. So when a payment transaction happens, it says, hey, is this the correct amount? If so, then he says, ransom contract, give me the encrypted key. So what is stored in the ransom contract is a wrapped key. So in other words, there's an AES key that itself is encrypted using public key cryptography. So the ransom contract calls back into the escrow contract at this point with that key and says it's calling this decrypt key. And at that point, the escrow emits the decrypt event. And this is where our crypt oracle then comes back into play. It sees, I see a decrypt event. It has, of course, the attacker's private key. So what it does, the other thing I failed to mention is the victim, and this is also, again, goes back to how do you increase the likelihood that your victim pays the ransom. The victim gets to choose a file of his choosing that is encrypted and present that with his ransom payment. So that's where the attacker has no idea what file the victim's going to give as the test file. And so that gives the victim a little bit more assurance that that if the oracle claims, for example, that it couldn't decrypt or it does decrypt, that it was actually true. Because bear in mind, other people on the blockchain could also see if the oracle was screwing people, and that would obviously determine whether or not it was a legit oracle or not. So in the decrypt event, it emits the wrapped key and this file presented by the victim. It tries to unwrap the key and decrypt the file and validate, I think it was either an HMAC or digital signature. And then it calls the decrypt callback in escrow with either, yep, it succeeded, or no, it failed. And if it succeeded, it writes the encryption key back into the escrow. The attacker at that point gets the victim's money, because then at that point it succeeded. If it failed, then the money is sent back to the victim gets their money back that way. And then at the last end, then it fulfills the contract at the very last step. And so, so the way to defeat this, let me see what's up here. Yeah, so this is the decrypt callback function in the escrow. One of the things that well, I don't want to say unique to smart contracts, but it's definitely a major issue in smart contracts, are reentrancy vulnerabilities. And what I mean by that is where if you're a smart contract and you call another smart contract, you've completely lost control of what happens next. In this case, right, the escrow is calling into that ransom contract. Now he expects, because the attacker wrote the ransom contract, that it's going to call back with that decrypt event and then be done. But there's no guarantees of that, right? If you call any other contract, and that's where some of the, if you Google around online, you'll see some examples of vulnerabilities that people have exploited, where some reentrancy type vulnerabilities that can result in contracts getting drained and losing out of money because of these types of vulnerabilities. But a couple of things to note here in the decrypt callback is that when the callback, first thing that happens is the ransom amount that was paid is just subtracted from this escrow amount. And then you can see that if the auth result was true, that the owner gets it and it fulfills, otherwise it gets transferred. The amount that gets transferred back to the victim is this ransom amount. Now the key thing to take note of, though, is that this is that ransom amount that we set in, or we had the ability to set by deploying our own ransom contract. Now there are a bunch of checks in the code, asserting that the payment amount and everything was correct. But one of the things that you can do, I think this is, yes. The thing that you can do to exploit this reentrancy vulnerability is essentially after you've called this decrypt key, you then call register victim right after that. So normally the escrow contract, right, is expecting it's going to emit this decrypt event, and where the checks happen for the ransom payment are here. When you call the pay ransom, it's checking that everything you've paid the actual amount. So it calls in the ransom. But now that it's called into our modified ransom contract, we have control, and so when we call back into the escrow, we do call decrypt key, but then we call register victim to overwrite that entry. But now we can overwrite it with the max value of that contract. So you could set it initially. You can register a ransom contract for a $0 amount. You do the pay ransom. It calls back into your manipulated contract. You call decrypt key, but then you immediately call, because bear in mind, when these calls between contracts, these are all part of the same transaction on the blockchain. So that there's a class of vulnerabilities known as TOC2, time of check to time of use. And these are race conditions. And there's a race condition in this whole process because the Oracle, when it's calling back with its result, that gets mined as a separate transaction. And so you can effectively, it's a combination of a reentrancy vulnerability and this TOC2 vulnerability where you're able to re-register. So you do the payment with a $0 amount, so it accepts it. Yep, he paid 0. Now, if that was the end of it, you saw in the code I had earlier, it just subtracts whatever you paid. So subtracting 0, that's not going to get anything back. And so this is why you need to register the victim afterwards, register it with the max value of the escrow, give it a bad file so that you know it's going to fail decryption, and then when the Oracle calls back in its separate transaction, it's going to say, hey, decryption failed, and then the contract is going to just pay you whatever ransom amount is in there. And in this case, you've set it to be the max ether that was on that contract. So at that point, all of that money is transferred back to you. And then the final part of the task was essentially paying out to all the victims that had paid into the contract. So it's kind of an interesting scenario, I thought. It kind of highlights, looking at the code looks fine if you just analyze it in isolation. I mean, there's checks all over the place. But at the end of the day, where things broke down was, this trust relationship between the escrow and the ransom contract, and you being able to have the ability to effectively control certain values and exploit this race condition with the Oracle here. So if you want to know more details, Jonathan does a pretty detailed analysis. He actually outlines a few other approaches. There's there's an integer underflow and a few other things that you can do, other ways of trying to go about this problem. But this was sort of the main process that we expected most people to go through. So any questions on the ransomware? Actually, I didn't even check the Slido app. Let me see if there's any. I don't see any. All right. Well, if there's no other questions, then we can call it a day. If you have any other questions, random NSA questions, I'm happy to answer those as well. So use me however you want. All right. Well, thank you very much.